One of the most important things we need to talk about in this chapter that is focusing on quadratic things is we need to talk about the graphs of quadratic functions. The reason why this is so important is not everything makes a straight line. When you're in Algebra 1, the only graphs that you really draw are graphs of straight lines, but honestly, that's like the shallow end of the swimming pool where the little kids play. It's not the reality of most graphs. Almost every graph that matters in the real world is jagged or curvy in some sort of a way. They don't all just make nice, clean, straight lines. Quadratic graphs are the first example that we can look at of something that doesn't make a straight line and that still isn't too complicated. So first of all, if you have an x squared in your function and you're ending up with a quadratic graph, the type of a curve that you get there is a shape called a parabola. And parabolas have two different orientations. They can point vertically like this one where they curve upward, or they can point downward to where the arc of the parabola could look like this. That's also a possibility as well. So be aware that parabola describes two things that you might think are really different, like an arch shape versus a U shape, but they're really the same shape, just one's upside down version of the other one. When you are talking about a parabola, there's a lot of related vocabulary, and these vocabulary words are often used to talk about the answers you're supposed to produce. Probably the most important vocabulary word about quadratic graphs is this first one. It's the word vertex. And the vertex is the point on the graph where it turns around. Like here, the graph was going down, now it's going up, so it's the lowest point. Or if your parabola points downward, it could be the highest point. And if you're asked to find the vertex of a parabola, that's a point. It has two coordinates. And for historical reasons, the x and y coordinates are not called x and y. We call the x and y coordinates of the vertex h, k. You're going to see the same thing when we talk about like the center of a circle or etc. You know, any sort of a shape, sort of the central point of the shape is usually called h, k. Another related idea to that is the axis of symmetry. And the idea is vertically right through that vertex, the left and right halves of the graph are supposed to look the same. They're supposed to be mirror images of each other to the left and to the right. So there should be a vertical line right down the middle of the parabola that is the line of symmetry. And since it's a vertical line, the equation for it should be x equals something. And it's not just any vertical line, it's got to go right through this point. It can't be over here or over there. It's got to be a vertical line going through that point. So if it's going to be x equals a number, the number it has to equal is h. So if you find the vertex, you should almost instantly be able to say what the axis of symmetry is. That should be, it's just part of the same information. The other kinds of things that you're asked for are intercepts and then the maximum and minimum value. The x-intercepts, as usual, are points on the x-axis. So their coordinates are going to have to be something, 0. And typically, the way you find them is you set the equation equal to 0. Because, in a sense, what you're kind of doing is you're kind of plugging in y equals 0. And if the whole equation is equal to y, and y is equal to 0, then the whole equation is equal to 0. And then you solve using factoring or the quadratic formula like you would normally solve for. And then the y-intercept is the place where the graph crosses the y-axis, so that's going to be 0, something. And that's a lot easier to deal with because you just plug in x equals 0. And that doesn't require you to solve any sort of quadratic equation. Usually it requires just a little tiny bit of arithmetic. So that's fairly simple. And then the last bit is kind of tricky because there's some vocabulary here that in math we use with a very specific intention that you might not be aware of. When you say the maximum or minimum value, what that means is the y coordinate at the highest or lowest point. Maximum for highest point, minimum for lowest point, of course. But the value is a y value. Y equals something. And if you look at the picture visually, the minimum for this picture is right there at that vertex. If the parabola was pointing the other direction, the maximum would be at the vertex. So whether it's a maximum or a minimum, the maximum or minimum will be at the vertex. And the y-coordinate at the vertex is k. So you'll notice that the vertex kind of feeds into the axis of symmetry, and it also kind of feeds into the maximum minimum value stuff. So as one piece of information, you kind of get three answers out of it, whereas the intercepts are kind of their own separate thing. They're not part of the vertex, so they're a little trickier to deal with. When you are working with these problems, there are two formats that are things are typically presented in. One of them, the one on the left there, is what's called the graphing format. Mostly because it's fairly easy to graph if things are in this format. And the other one over here, for some reason, is called standard form. You can see why it's called standard form. It's sort of the way we typically write polynomials, with everything all multiplied out and cleaned up in the instinctive way you've been trained to clean things up. Notice that graphing format isn't what we would normally call simplest form. Standard form is what we would usually call simplest form. But here's the thing. If you are trying to graph this thing, you're almost always going to start by figuring out where the vertex is. And if things are in graphing format, your vertex is right there. That letter H and that letter K, I didn't accidentally use the same letters that I used for vertex. I deliberately used the same letters I used for vertex. The vertex is at HK. Which means you don't have to do any work at all to figure out what the vertex is when it's in graphing format. On the other hand, when it's in standard form, figuring out what the vertex is a lot trickier. The x-coordinate of the vertex is going to be at negative b over 2a. And if you're having trouble remembering that little formula there, it's basically the same as the quadratic formula, except you throw away the square root. You know, that plus or minus square root of b squared minus 4ac. Throw that away, and what you have left is that. That's only the x-coordinate. To get the y-coordinate, what you have to do is plug in x. The x you just got out of using that little shortcut there, you have to take and plug x into that, and of course, there as well. Solve, do all the arithmetic. So that's a lot of work, whereas in graphing format, it's sitting there right in front of you. So between the two techniques, people typically prefer graphing format. Once you know where the vertex is, the next thing that you want to know is whether the graph curves up, like the example I have on the screen here, or whether it curves downward, which is also a possibility. And there's a really quick and easy way to tell whether it curves up or down, and it's the same whether you're in graphing format or standard form. In either case, if you want to know up versus down, it all boils down to the letter A. You know, A. The same letter in both of these, the letter that's in front of the parentheses there, that's in front of the x squared here. If A is bigger than 0, then the graph is going to curve upward. If A is less than 0, the graph is going to curve downward. And there's a real easy way to remember this. I mean, it's so simple to remember. Just remember that bigger than 0 means positive, and less than 0, the word for that is negative. And think about these as emotions. If somebody is feeling positive, don't they smile? And if somebody's feeling sad, don't they frown? Wait a sec. Hold on. That's not how you draw a frown. That's just an upside down smile. Upside down frown still has the eyes above it like that. So, if somebody is positive, if your parabola is positive, it smiles, which means it curves upward. And if your parabola is negative, then it's frowning and it curves downward. Very easy to remember. There's another thing that A tells you that's a little trickier, and that is if A is a big number, and that's kind of tricky to define. What is a big number? Well, what we mean by big is the bigger it is, the more this thing happens, and the normal size is 1. Like 1x squared is kind of like the average size. So bigger than 1, and then like 2, 3, 4, 5, 10, 20, 1,000. Those numbers are big. Then what happens is your parabola gets tall and narrow. You get a parabola that's been sort of stretched upward and very sharp at the bottom. On the other hand, if A is small, and again, I put that in quotes because what do we mean by small? Well, we mean smaller than 1. And the smaller it is, the more this happens. This produces a very wide parabola. It's sort of like you mashed it downward, so it ends up being squished out sideways. So big values for A, things tall and skinny. Small values for A, it's wide. Oh, but wait a sec. It could also be negative. So there's this weird little technical thing here that you wouldn't understand until I kind of show you the connections here. Remember, it could also be pointing downward. And if we have a big negative number, that's technically small. So to just avoid that whole thing, we typically put absolute values on this. So if A is negative 10, then absolute value of A is 10, and you get a very skinny parabola. If A is negative 1/3, the absolute value is 1/3, and you have a small coefficient. It's a small, wide parabola. Okay, let's put all this stuff together and do an example, because this really won't make sense until we're actually doing an actual example. So, let's say you were asked to graph something like this. Your first step is to figure out where the vertex is. And remember, there's an actual shortcut, negative b over 2a, and then plugging in that you would have to use if it was in standard form. But in this case, it's in graphing form, so the vertex is very easy to figure out. Well, it might not be as easy as you think it is, because the plus and minus signs are a little tricky. Scroll back into the video and take a look at the way the setup is. H, in this case, is not negative 3. H is just 3. Whereas K is negative 1 here. So our vertex is at 3, negative 1. Watch out for the signs. They're a little tricky. The H part is the opposite sign, but the K is the same sign. And then, which way is this thing going to point? Is it going to point up or down? Well, A is 1/2. 1/2 is bigger than 0, so that's going to point up. We're going to get a parabola shaped like this. But A is also kind of smaller than 1, so it's going to be wide and pointing up. And then you go to graph this thing and you realize that's not enough information. Well, it could be enough information. And this is one of the things that's a little tricky about this section of the book here. When we say, where's the vertex and which way does it point, why do you want to know this? Well, maybe you're solving a word problem where this is related, and the fact that it points up instead of down might be all you needed to know. Or the fact that it's wide instead of narrow might have been all you needed to know. So perhaps you're matching the equation to a list of graphs. And if you can say, okay, it looks about like this, it's kind of a wide parabola, maybe that's enough to pick out of, I don't know, 4 graphs which one is the right graph. So sometimes this is plenty of information. Sometimes this is all you need to know to answer a question. But there are plenty of other times where you need to have a very exact, careful graph. And if you're trying to get an exact, careful graph, what you have to do is a table of values. And we already know what happens when we plug in 3. We get negative 1. So the rest of the points that we want to be plugging in here, they should be numbers close to 3. So don't start plugging in 0 and negative 1 and negative 2. Those are way off to the side. Try plugging in 2 and 4. Or 1 and 5. You know, numbers that are close to 3. So if I plug in 2, well, now that's actually going to be quite a bit of work. It's going to be 1/2 times 2 minus 3 squared minus 1. So 2 minus 3 is -1. Squared is +1. A half times 1 is half. Half minus 1, we get -1/2 there. So 2 comma -1/2. That's not impossible to graph. A similar thing happens when we plug in 4. 4 minus 3 is 1. 1 squared is 1. Half times 1 minus 1. We also get -1/2 there. Oh yeah, that's right. It's supposed to be symmetric. You really shouldn't be surprised when these graphs come out with the same numbers on either side. If they don't, something's wrong. Maybe you have the wrong vertex, maybe one of your points is incorrect, but it's supposed to be symmetric on the left and the right. Let's try plugging in 1. So we get 1/2 times 1 minus 3 squared minus 1. -2 squared is 4. 4 times 1/2 is 2. 2 minus 1 is 1. So we get that point there. Similar thing happens when you plug in 5. 5 minus 3 is 2. 2 squared is 4, etc. You also end up with 1 over there. And we can keep plugging in more and more points to get a more and more accurate picture. And how many points you do? It depends on how much accuracy you need for whatever sort of thing you're being asked to do. If you're being asked to pick between a couple of graphs that are different widths, you might need this many points. If you're asking to know where it crosses the y-axis, you might need to plug in 0. If you want to know some points up here, we haven't plugged in enough. So I cannot give you a solid single rule for how many points you have to do. It depends on what you're being asked to do.